We're going to end this class talking about multiple regression. So before I move forward, I really want to focus on the fact that what we've been looking at is statistical techniques, and that the ANOVA and the factorial ANOVA are both based around the idea of an advanced technique that can look at multiple levels or multiple independent variables, all predicting the same DV. But it's also a little more simple because the IVs are always going to be categorical with an ANOVA, and that's what ANOVA is designed to do. Now, if we actually have multiple predictor variables, multiple independent variables, and they're not categorical, that's where we'd have to move to multiple regression. Now, multiple regression lives at the end of this class because it's not a technique that we're going to do a deep dive on. We're not going to be learning how to do it in SPSS. We're not going to be really talking that much about the mathematics. But what I'm wanting to do is to kind of give you an idea of where you would go after ANOVA. And the multiple regression in many ways is the kitchen sink, if you will, of statistical techniques. You can do just about anything with multiple regression, assuming you're predicting a single continuous outcome variable, a single DV that's continuous. So the difference between simple and multiple regression is simply that we have more than one predictor, and they are continuous. But even that comes with a caveat. We're going to talk about, much like an ANOVA, when we run an ANOVA with multiple IVs, we get multiple F-tests. For each IV, we get the question of, is it significant enough? And then we get whether or not the interaction between those two variables is significant. Again, the 2x2 ANOVA. Multiple regression is similar. When we have multiple predictors in the model, we're going to get a regression coefficient, an R, if you will, for every single predictor and every single possible interaction. Now, multiple regression, just like simple regression, also will give us information that we can use to create a predictor variable. In other words, we can predict future variables from multiple regression. And again, we're going to get the same thing we got with a simple regression. We're going to get B weights, we're going to get an intercept, and we're going to be able to create the equation, except this time every significant predictor will add to that equation. We'll have multiple B weights and multiple predictor variables. We can also use multiple regression to look at categorical variables. Now, this is not the optimal thing to do. When we normally do this is pretty much where we're in a situation where we have some continuous variables and a categorical variable. Well, in that case, we can't use ANOVA because ANOVA can only look at categorical variables as the independent variable. Therefore, we'd have to use multiple regression. But multiple regression, by its design, can only look at continuous variables as IVs. Actually, there is a fix around this, and we'll talk about that as well. How to do kind of a mixed multiple regression with both continuous and categorical IVs. We can also look for nonlinear trends. So remember that simple regression is limited in that you have to have a linear relationship. In other words, the relationship has to basically fit to some degree a line. Multiple regression has that assumption. However, if you know that you have a nonlinear design and you know what kind of relationship there is that's nonlinear, you can actually program, if you will, multiple regression to look for higher order trends as well. In other words, nonlinear trends. Finally, we can look for interactions. And unlike ANOVA, with multiple regression, we're a little bit more in control with what we're doing with those variables. We have to tell multiple regression to look for interactions, which means that often we may be comparing multiple models. So what I mean by multiple models, you may have a multiple regression that uses all 4 of your predictor variables, 4 continuous IVs. You may actually find that a better model just uses 2 of them, and therefore you want to analyze that as well. So we're also looking for the simplest method. So when we're using multiple regression broadly, the first thing to keep in mind is that if you can use a different statistical technique than multiple regression, you should do so. Because if there is a specific technique that's been designed, it's probably been designed to be a better estimate, a more accurate estimate of probability than multiple regression. But if you have a model or design and your independent variables and dependent variable don't fit anything else, probably multiple regression is your answer. And finally, when we run a multiple regression, we're not just asking, is each predictor significant? We're asking, which interactions are we interested in? Are there any actual nonlinear trends we're interested in? And finally, at the end, we're asking, what is the best model that explains the data? So we're not always going to get the exact same results when we run a multiple regression. So generally speaking, we're not going to worry about the math behind it. About the only equation we're going to talk about with multiple regression is the predictor equation. And you may notice it is very similar. We still have y prime, what we're predicting. That's the dv we're predicting. And just like simple regression, we're going to start with the y-intercept. And then we're going to have that first beta weight times the first predictor. The only thing we're going to add is for every predictor or every significant interaction, we're going to have a b weight for each of those variables or each of those interactions, and we then add in, to do the equation, the individual person's score on each of those predictors. So it basically just expands the exact same equation we've already used. So when we're comparing simple versus multiple regression suggests that there are two or more predictors, two or more independent variables. And these independent variables can include, as I've already mentioned, linear trends. So that's actually, we don't have to do anything for that. So if we have two predictors, they're both continuous, and we both expect them to have a linear trend with our dependent variable, that's where multiple regression just basically, we just plug and chug. We could also define some of those independent variables as not independent variables, but covariates. So covariate is when we take a variable and we decide it's not an outcome variable, it's not a DV, it's not an independent variable. We're not wanting to use it to predict, but we think it may be related to our outcome, our DV. Now that might sound a lot like a confound, and in many ways it is. What a covariate refers to, though, is a confound that we pre-predict exists, we pre-measure it, and if there is a relationship, we actually can now remove that relationship because we've measured it. So let's say, for instance, that you're really not interested in gender differences in a particular prediction. In other words, yes, there might be gender differences, but I'm wanting to ask, does this model predict behavior regardless of whether you're male, female, binary, non-binary? So I might actually measure gender, include it as a covariate, and it would be entered similar to an independent variable, but I would remove that variable, that variance, for my final analysis. Like I said, it's made for continuous variables, but we can actually use categorical variables in a multiple regression. And the way we do that is actually dummy coding. So when you hear the term dummy coding for multiple regression, it's referring specifically to categorical variables. Because just like simple regression, if you remember when we were talking about simple regression, I mentioned that you could use a categorical variable for either correlation or simple regression as long as it was binomial, basically had two levels. It was a binary categorical variable. And that is still true. Now, with simple regression, we can only have one IV. Therefore, the only categorical variable we could ever use in a simple regression or correlation would be a dichotomous or two-level variable. However, because multiple regression allows me to have more than one IV, what I can do is called dummy coding. So let's say I had an independent variable that's categorical with three levels. I would not enter that variable unchanged into the multiple regression. I would dummy code it. I would have a variable for 1 or not 1. I would have a dummy code for 2 or not 2, and I'd have a dummy code for 3 or not 3. And in that way, I'd create dichotomous variables, two-level variables, out of my multiple variable categorical variable, my variable with more than 3 levels. So I would not actually just be dumping a categorical variable into a multiple regression. I'd be dumping multiple versions of that categorical variable, dummy coded into two-level categorical variables. As I said, we can look for nonlinear trends, trends that are not linear relationships, and finally we can look at the interaction between multiple variables. Now again, additional predictor variables means we must now consider how those predictor variables relate to each other as well as the outcome. So again, it starts to get very complex when we're running multiple regressions, especially with those interactions. So the regression coefficient is basically, again, so for each individual predictor, we're going to get an R, we're going to get a p-value of, is it a significant predictor of our outcome, our DV. In addition, once we know what's significant, we can create a prediction equation with multiple regression. So we can add second, third, fourth independent variables, allowing us to test the relationship of additional predictors on the dependent variable. So for instance, if I was wanting to look at GPA and ACT scores, predicting high school GPA or college GPA predicted by high school GPA and ACT taken during high school, that'd be two predictors. So again, to predict my Y, I would have my intercept, which I'd get the same way I'd get with a simple regression. I would get a B weight for ACT score, and I would get a B weight for high school GPA. So I'd take a person's score on the ACT multiplied by the B weight for ACT. I'd get their high school GPA multiplied by the B weight for high school GPA, and then I'd add that to the y-intercept. That would give me my prediction. And again, we can add as many predictors as we want, so it can go on for quite a while. And sometimes what we're asking is are we getting better and better prediction as we move along? And we're going to talk a little bit about model selection with multiple regression, and that's what model selection is about. At what point does adding predictors really not give you any additional bang for your buck, if you will? In other words, at what point do we, we're still adding significant predictors, but our actual ability to predict is just not getting any better. And that's really where the model selection comes in. When do we want to stop, especially if we have a whole bunch of predictors? And that's one of the things multiple regression will tell us too. The model selection process is telling us when to stop adding predictors. So when we're adding additional predictors, do consider that like all statistical techniques, there are issues. And the big one is power. Every time we add a predictor, we're reducing the degrees of freedom overall for us to be able to claim statistical significance. Generally speaking, we want to add 10 subjects per variable. So if I was running a multiple regression with 2 predictors, high school GPA and ACT, predicting college GPA, I actually have 3 variables. I'd want a minimum of 30 subjects in that study, and probably, honestly, I'd probably want 60. 10's kind of a minimum. I would say you're probably aiming for 20. So if I got a very complex model, let's say I was wanting to look at letters of recommendation, ACT, high school GPA, and also personality. So there's 4 variables. And an outcome being college GPA. That's 5 variables. That means I'd need a minimum of 50 subjects, and I'd probably want 100. So again, as we add predictors, we also create larger and larger studies. The second issue that we really want to consider when we're running a regression is the concept of multicollinearity. Multicollinearity is a reference to when an independent variable is related too much to another independent variable. It basically means they're really measuring the same thing. And when this happens, it actually makes multiple regression not just less predictable, it also makes it almost unstable. Because the process of multiple regression is, again, a process of assigning variance. It's assigning the variance that it's finding. It's assigning the related variance between each IV and the outcome, the DV. If you've got 2 variables that are highly correlated with each other, in other words, you've got 2 independent variables that are very much related to themselves regardless of the DV, and both of them are related to the DV, you may get some very weird results because, again, multiple regression doesn't know where the overlap is. It's going to have to assign that variable, that variance, one place or another. So for example, if we look at the top example, yellow is my outcome, and I've got 2 predictors, X and W. And both X and W are somewhat related to each other, which is not surprising. Let's say that they're conscientiousness and openness to expression. So the red area is the overlap. And again, when multiple regression occurs, it's not necessarily going to assign that to an interaction unless we ask it to. If all we told it was, hey, how much does X relate to Y and how much does W relate to Y, it's going to basically give blue to X. It's going to give green to W, and it's probably going to assign red to either X or W. Generally speaking, whichever one it seems to be a larger part of is where it's going to go. But that means that we're probably going to get an artificially inflated independent variable relationship with X and W, for example, if X gets red, and a slightly reduced variance of how much W is related to Y compared to how much they're related to Y in isolation. If X and W are highly related, notice that red section of the bottom graph gets a lot larger. So now, for instance, we might actually find that if the multiple regression decides X, and by decides, I mean where the math takes it. And generally what it's going to happen is the way multiple regression works is if X is 1% more related to our outcome than W, it gets first crack at the variance, which means that X would get blue and red. And what we might find then is that W actually is no longer significant. In other words, X is the only significant predictor. Green is not big enough to actually award W significant impact on Y. However, if we didn't measure X in the first place, W would have been a huge predictor of Y. And that's why we need to test for multilinearity, and generally kind of a rule of thumb on multilinearity. If you've got two independent variables that are correlated, so just simple correlation of over 0.9, probably you need to only include one of those. And including both of them will make your model, quote unquote, unstable. You're not going to get information that necessarily makes sense, always. So predictive variables can be entered into the model several different ways, and this is definitely an area where multiple regression differs from other statistical techniques that we've talked about. When you run a factorial ANOVA, it always treats the data the same way. Not so with multiple regression. You can treat multiple regression kind of like an ANOVA, and that's what we call standard entry. That means that you basically put every single predictor variable in at the same time, and SPSS basically figures out which is the strongest predictor, gives it variance first, second strongest variable gets its variance second, etc., until there's no more variance to assign to IVs. It's a common method when all variables are deemed as equally important, or if you really don't have any standard or hypothetical or research-based reasons to believe that certain variables may be more important. More often, you'll actually see what's called hierarchical regression. You actually assign succeeding variables by providing the predictability or accountability, so you're in charge of it. So we might use this when some variables are covariates. We might use this if we're looking for interactions, or if we're using it with a theory-driven model. What this looks like is, let's say you have three predictors. You've got college GPA, you've got GRE, and you're trying to predict graduate school performance. What's that third predictor? Well, that's the interaction between the two. Now, let's say that you're not concerned with gender. In fact, you don't want to account for gender. Gender is a covariate. So now I've got a predictor, college GPA. I've got a predictor, your GRE score. I've got an interaction, GRE score by college GPA. And I've got a covariate, gender. I might actually put gender in first. And I'm telling SPSS, I want you to figure out what part of variance of the outcome of college or graduate GPA is gender. Once you've identified it, remove it. I don't care about it. I then might want to put in my two individual predictors in what's referred to as a block. So in other words, the first block is my covariates. The second block is the individual predictors by themselves. And the third block would be, is there an interaction left? And that would look a lot like an ANOVA. Basically, I'm saying remove the covariate, look for my main effects, and then look for my interactions. But if I had a theory-driven reason to believe my interaction was actually very likely and more important, I could actually put the interaction first and say, hey, don't see if there's an interaction above and beyond my IVs. Look for the interaction first and then see if there's anything left for my main effects. We can change the order in regression if there's a theoretical reason to do it. And finally, there's basically more statistical prediction, and these are systematic techniques, forwards, backwards, and stepwise. And generally speaking, what we're looking at here is forward regression means I start with my largest individual predictor of my DV, and I assign it variance. I then go to my next one, my next one, my next one, my next one. So this may sound a lot like standard regression, except that forward regression can also be used in blocks, a hierarchical model. So if we were not using a hierarchical model using individual blocks of entry, and we ran a forward regression, it would look a lot like a standard regression. Now, backwards regression means I'm going to start with all of my predictors in the model, and I'm going to start pulling them out until I significantly reduce my power to predict. Both of these techniques are not necessarily about checking the significance of every predictor, which is standard. It's more about when can I stop adding or when can I stop removing. Stepwise basically just does both of these. It goes forward and backwards to get to its results. Now, when we're looking at this, there is differences. If we enter all at once, we're using the enter method. If we're using a hierarchical model, we can enter variables in blocks. And if we're using the backwards, forwards, or statistical techniques of stepwise, all three of these are going to look at variance differently. And for example, if we're looking at GRE, GPA, your statement and CV on graduate GPA, if I look at the enter method, I may find that these three are significant and statement is not. If I use a hierarchical model, or this is backwards regression, I might find the CV isn't important. It's statement, GPR, and GRE that's important. So again, just remember that the methods that we're entering the data is going to be looking at things differently in how they proportion actual variance. And that's not even including nonlinear or covariate trends. So here's another example. Again, we have three predictors, x1, x2, and x3. Each one of these circles represents all of its variance. Y is our variable that we're predicting. In enter method, enter is looking for unique variance based on the size of the relationship. So if I was using the enter method, it would basically predict that x3 is responsible for the pink section, x2 is responsible for the green section, and x1 is responsible for the blue section. It would ignore the variance that's being explained in our predictor by any interaction or any combination. It's looking for unique variance. And that's why it's a really good technique just to find out which individual predictors may be important down the road. That's what it's looking for. Hierarchical, I might tell SPSS, I want you to put x1 in first. In that case, it's going to get all of the variance that's explained by x1 on y, whether or not it's related to other variables or not. My second block might be predictor x2. And it's going to get all that remaining variance. It's going to get the green. And then finally, x3 is allowed to go in. Now you can tell if I had gone in the other order, x3 would be the stronger predictor, followed by x2, and x1 would be the weakest predictor. So the order does matter because all that variance is there, but where it's getting assigned is up to me when I use hierarchical regression. Forward method is still going to look at total variance, but it's going to basically first ask what is the biggest predictor, and that very well may be x3 is the largest predictor, so it gets all the variance first. So I'm no longer in charge of this. It's simply asking what's my strongest relationship. That's who I'm going to give the variance to. Then I'm going to go to x1, and then I'm going to go to x2. So again, with predictability, multiple regression can make equations that predicts a DV on more than one IV. Multiple regression can often create better predictions since you have more information, and it's usually more accurate. So if all I was trying to do to predict graduate school success was GPA, that's the only predictor I'd have. But if I had GPA, GRE, letters of recommendation, and statements, all of those together would probably add and give me a better predictor of how someone would do in grad school. Now, we did talk briefly about how you can basically take categorical variables and put them into a multiple regression. And again, if it's nominal, a dichotomous variable, values are simply coded as 1 or 0. 1 present, 0 not present. 1 a history of alcoholism, 0 no such history. 1 male, 0 female. However you're actually defining it, generally we're going to code it as zeros and ones when we put it into a multiple regression. It's just a little easier to keep track of. Now, if we actually have a categorical variable with more than 2 levels, we're going to create dummy variables, where k is the number of possible levels. And basically speaking, it's k minus 1 creation. So if I've got 3 variables, I'm going to have to make 2 dummy codes. And what I'm going to do is basically 1 or not 1, 2 or not 2. But I'm going to code them as ones and zeros, ones and zeros. So if you are a 1, you would show up as 1 in the first column. Or if you're not 1, you'd show up as a 0. And the second dummy code, if you were a 2, you would show up as a 1. And if you weren't a 2, you'd show up as a 0. Because I now have 2 columns, there's basically 3 possibilities with those 2 columns. You could have a 1 in the first one, that means you're in category 1. You could have a 1 in the second one, that means you're in category 2. Or you could have 2 zeros. If you have 2 zeros, you're in the third category. That's why we only have to make k minus 1 dummy variables when we put them in multiple regression. We're going to get the information we need, regardless of how many levels it has, by the number of levels minus 1. Dummy variables recode variables as present or not present for each possible level. So example again, if my IV is religion, at that point my levels might be Christian, Buddhist, or Hindu. So again, Christian, 1 or 0. You're either a Christian, you get a 1. If you're either anything else, you're a 0. You're either a Buddhist or you're not a Buddhist. If you're a Buddhist, you're a 1, anything else is 0. And anyone that's scored as 0, 0 would be therefore coded as a Hindu. Now again, this is a lot to take in. And my goal is not to make you a master or even ready really to do multiple regression. I really want to stress that I'm just kind of walking through everything that we can do with multiple regression and at least kind of introduce you to some of the problems with multiple regression. It's one of the reasons that we want to use other techniques if they're available, because most of the other techniques are designed to do very preset things. Multiple regression is designed to do just about anything, but that also means we have to make some pretty interesting choices that aren't present in any other statistical technique. What kind of model we're using, how many variables we're putting in, what order do we want those variables to be analyzed? Do we want to use a hierarchical model? Do we want to use a statistical model like forward, backwards, or stepwise? Or do we just want to use an interstandard model? All of these are choices we have to make, and we'll have to defend when reporting these results. Also recognize that though we can look at categorical variables, if I've got a categorical variable of 3 levels, I'm having to dummy code it into 2 levels. That means that I'm losing power. I'm basically making it 2 variables instead of 1. If I had a categorical variable with 4 levels, 4 minus 1 is 3, that means I need 3 dummy codes. That means I now have 3 variables that I'm having to put into my model. And remember, for each variable, we're having to add 10 to 20 people to our study.